Okay, so we talk about cryptanalysis on stream cipher, attack on stream cipher. Especially we will talk about algebraic attack on stream cipher. So let us just recap what is a stream cipher. We have seen the LFSR based stream cipher. Basically, in stream cipher we have a key stream generator. Key stream generator. This is basically a pseudo random bit generator because the bit it is. So we have a so this is basically taking initialized by the initial key. So the key secret key K, which is shared between Alice and Bob. So we have two party Alice and Bob. So they have a common key. This is symmetric key encryption. They have a common key K, which is some bit. Now, if it is LFSR based stream cipher, then basically what we have a LFSR. Say for example, if we have a 4-bit LFSR and if this is 4-bit, and we have some connections over. So depending on the polynomial, we have some connections, and this is state transition. This is the way it change the state. So we have a feedback from this bit and this bit, and this is so. So it is taking the, so if K is 4 bits, say K0, K1 or the other way around. So K3, K4, K2, K1, K0. So we initialize this state by this way and we run the LFSR. So it will keep on generating the K0 first, come out, then it will be K1, K2, K3. Then it will be XOR with this K1 XOR K2, K2 XOR K1 like this. So then K1, so like this. So this is the key stream, and this key stream we are going to XOR with the plaintext bit P0, P1 like this, and we got the C0, C1 like this, and this C0, C1 will send to Bob. So this is the encryption. Now how Bob will decrypt it? So Bob is having the same LFSR, the key stream bit generator, and Bob is having the same key, which is the secret key shared between Alice and Bob. So Bob will just initialize the state by this key, and it is the same LFSR. So this is one example. So we can. So Bob will generate the same key stream bit K0, K1 like this, and Bob will XOR this with the C0. So Bob is receiving C0, C1, and Bob will get back C0. So K1 XOR with C1. So Bob is getting the plaintext bit. So this is the decryption which is doing by Bob, and this is the encryption which is done by Alice. Now we have to think of what Oscar can do. So now if Oscar knows some, so this is if this Oscar knows some plaintext and ciphertext bit. This is chosen known plaintext attack. If Oscar knows some plaintext and ciphertext, now this ciphertext is basically the linear function of the plaintext and the key. So basically what we have, so we have a ZT, which is the, so this is basically function of K is the secret key, and so ZT is the function of secret key, and it is basically what we are doing, we are getting the CT as ZT XOR with PT. Okay, now so ZT is the TF key from the key stream, and this is the TF ciphertext bit, and this is the TF plaintext bit. Okay. So now ZT is basically CT XOR with PT, Okay. Now zt is basically function of x, function of k. K is the secret key shared between Alice and Bob. So that is the initial phase. We are loading the secret key, and then we are running the key stream generator. So this is basically, so ct. Now if this function is a linear function, then basically we have some system of equation, linear equation, and then we can solve it to get this k. Once we get the k, then everything is gone, because k is the secret shared between Alice and Bob. So that is the attack on simple LFSR based stream cipher. So to avoid that, we need to put some nonlinear function in the LFSR based stream cipher. So some nonlinearity we need to introduce. So that is why we say we have say LFSR, L1, L2, like say, so n many LFSR, and these we are passing to a function f, nonlinear function. So this is our dot. This is our key string. This is our key string. So what we are doing? So this LFSR is having same length. So this is Alice is doing. So this is the encryption Alice is doing. So what Alice is doing? Alice and Bob, they have shared with a common key. So they are loading this secret key in each of these LFSR, and then they are running this, and they are getting some output from this LFSR. So this is x1, x2, x2, x3 like xl like this. So this is basically a function of x1, x2. This is a Boolean function. So it is basically a function, f is a function of 0, 1 to the power n to 0, 1. So this is a Boolean function. We can realize this function in an algebraic form, or we can have a truth table for this function. So we can have a truth table like say we have these values x1, x2, xn, and we have this value z. So this is the z, the key string. Okay. So we can have all possible combination of these 0, 0, 0, 1. So we can have the output. So we can explicitly have the truth table for this function to represent, or we could have a algebraic form, like we can have this function to be say x1, x2, XOR with x2, x3, x4, like this. Okay. Now we call this function to be balanced. If the number of zeros and number of ones are same, then we call this function to be a balanced function. And this function we want to be a nonlinear function, because these are the nonlinear terms, and this will make this will make our cipher to be secure in the terms of the algebraic attack, because we are not able to find the linear equation out of it. So we'll see how we can try to get a linear equation by linearization of these terms. So that we'll see. So this is the general form of nonlinear. This is a nonlinear function which is taking the input from the linear LFSR and which is generating the output. Now this is the key stream we are getting, and this key stream we XOR with the plaintext bits to get the ciphertext bits. So this is the encryption. So decryption, Bob is doing the same thing. Bob is having this structure. So what Bob will do? So Bob will just put the same secret key shared between Alice and Bob, and then Bob will run this key stream, and Bob will XOR this key stream with the key stream bit with the ciphertext bit, and Bob will receive the plaintext bit. Okay, so this is the general structure of a LFSR base, but any stream cipher so for any general stream cipher, this is synchronized stream cipher. So any stream cipher, what we have a key string generator, or this is called pseudo random number generator. Pseudo random number. Why pseudo? We know why pseudo, because it cannot give a truly random sequence. So that's why it is basically it is a finite state machine. Okay, so this is taking input as we initialize this state as this state we denote by st, where we initialize this by the secret key k shared between Alice and Bob, S0. So these states are initialized by the secret key shared between Alice and Bob. And then we have a state update function g, which is taking the current state g of st and which is generating the next state. Okay, where s0 is the k. So this is the state updating function. For LFSR, it is the feedback function. So we XOR those bits which are participating in the feedback, and then we are taking the feedback in the last bit, and then we have another function which is taking the current state and apply a function h, or so this is giving us the key string. So h of st is basically zt. So the key string bit of the tth key string. Then we XOR this key string with the plaintext bit pt, and we generate the hypertext bit ct. So this is the general structure of a synchronized stream cipher, because here we are not involving the plaintext in this updation function or in this key string generation. That's why it is called synchronized. In the asynchronized, we'll see in the next lecture, we'll see some modern stream cipher. So there we will see there are some asynchronous stream cipher where the plaintext is also involved, also participating in the. So this is a function of the plaintext also. But here we are taking just a synchronized stream cipher. Okay, so can you go to the slide, please? Yeah, so this is the general structure of a stream cipher. We have a secret key, and we have a key string generator, and we are running this key string generator to get the key string, and this is the plaintext bits p0, p1, pn, and then we are XORing with this pi with the key string bit and getting the ciphertext bit. So this is the encryption what Alice is doing, and upon receiving this ciphertext bit, Bob is just having the same structure, same stream cipher, and Bob is generating the key string bit again by taking the initial value of the state as the secret key, and Bob is decrypting and getting the plaintext back. Okay. So this is, we have seen, if it is LFSR based stream cipher, we have n LFSRs which is taking the input to the nonlinear function f, and we are generating the key string. Okay, so this is the structure. So we denote this zt as f of xt. So xt is the state, so state updaters function. So in our example it was h, so basically g. So this is basically f we are denoting. So zt is basically this is h. So this is the key string generator. So we have we have taking this f, we are taking a state, and we apply this f on it, and we get key string. So now this f is for a LFSR based stream cipher, we know this f is basically updating the function. This LFSR has this updation function. So for all the bits, it is shifting the one position except the last bit, nth bit. So nth bit is basically linear feedback of these bits, depending on the polynomial which we are going to use for that. Okay, so this is basically, and the xt is basically, so we take a state. So basically what we have a, this is ST, this is the finite state machine. So it could be LFSR, or it could be a collection of LFSR, then we have a F, it could be anything. So basically you have finite state machine, and this machine, this is the state at time t. So this is our ST. Now it is applying a function f, and which is giving us zt. So zt is basically f of st. Okay, so this is the way we think that. So then we have then for algebraic attack, what we need to do, we need to write this zt in terms of this f in terms of algebraic equations. So expressing the whole crypto system as a large system of multivariate algebraic equation which can be solved to recover the secret key. So algebraic attack based on two basic strategies. They are basically, we construct a system of algebraic equations involving the secret key using some known plaintext and ciphertext, because this is a known plaintext attack. We know some plaintext bit and ciphertext bit. So basically what we are doing, this is the key. So our ciphertext bit is basically, TF ciphertext is basically PT XOR with ZT. So now if we know this ciphertext, if we know this CT and PT for some t, so this is a known plaintext attack. So if we know this, then what we basically do, then ZT is basically CT XOR PT. Okay. So now if this is known, if this is some value, then what we have basically, so we have basically some functions like, so we know this ZT is basically f of xt is basically some CT XOR PT. Now this value is known for some t. Now from here we basically have a system of equations. Okay, then we try to solve this system of equations. So this is the construct the system of algebraic equation involving the secret key, because S0 is the secret key. S0, which is this state, is initialized by the secret key. Okay, so this is the attack model of algebraic attack. So here what we are doing, we have a key stream generator, which is basically the finite state machine, which is a pseudo random bit generator. It is a finite state machine. So it is initialized by, the state is initialized by the secret key shared between Alice and Bob, and it is generating the key stream sequence serially, and then this key stream is XOR with the plaintext bit and generate the ciphertext bit and sending to the Bob over the public channel. Now upon receiving this ciphertext, Bob is doing the decryption like this. Bob is again generating the key stream, because Bob is also having the same pseudo random bit generator, and Bob is putting the secret key as the initial state, and Bob is running the same thing, and then Bob is XORing with the ciphertext with the this key stream bit and getting the plaintext back. Now what Alice is doing, so Alice is receiving this ciphertext. Now suppose Alice is having this ciphertext bit and a few ciphertext bit and the corresponding plaintext bit. So this is a known plaintext attack. Then basically Alice this if is having, the attacker is having this system of equations. So basically, so if the attacker knows n plaintext bit and the corresponding ciphertext bit, then he can construct the following system of equations. Okay, so this is basically, this is if it is a LFSR based string cipher, because these are the LFSR bit updates. So every state is initialized by K0. So this is basically this is the say for example, first if we know the first k, if we know the first k plain text and the corresponding ciphertext. Okay, so then what we have? We have this z of k1, which is basically f of L of k1 k0. This k0 is the secret key shared between Alice and Bob, or this is the private key shared between Alice and Bob. Okay, because this is coming from that, because we know that P1 XOR with C1, it is basically Z1 like this. So similarly we have X2, which is basically f of LK2, so like this. So these are all state updatance function for LFSR, but it could be general stream cipher. So this way we have n many this key stream, so it is corresponding to, so this is k0. So these are all function in k0. So this is a system of equation where this k0 is the secret key and L is the state update function for the LFSR, this L, and F is the nonlinear filter function used in the stream cipher, and xt is the key stream bit in the tth clocking, that means tth key stream bit. But it could be other than LFSR also, it could be general stream cipher. Then we have a finite state machine and it is updating. Okay, so now, so what next? So our next target, so we got some system of equations. Okay, so our next target would be to solve this system of equations, because this system may not be a linear system. If it is a linear system, we can directly use the Gauss elimination method or some matrix method to solve it. But this system may not be a always linear system. So we'll try to make this system to be linear system. So that is the method called linearization. So we'll talk about that. So the question is how can we solve this system? So there are some algorithms to find the solution of this type of system. One is linearization, we'll talk about that. Then relinearization, then Excel algorithm to solve this system of equations. So what is a linearization? Linearization is basic idea. Basic idea of linearization is to this linearize the total system by introducing the new variable in the system of equation and finally solve. So this system may not be a linear system. So we will just introduce some new variable in this system to make it linear system. We will say if we have a variable say x1, x2, this is not a linear, but we can put this as y1. So that way we will solve this. Now once we have a solution, once we solve it in terms of y1, then we will try to get the solution for x1 and x2. So this is called linearization. So then the maximum number of monomials can be present in the system of the equation with n variable of degree d must be less than equal to summation of I is equal to 1 to d n choose I. So to linearize one system of equation of n variable of degree maximum d, we need maximum this many number of new variables in the final system. So this variable, so this number should have control, because otherwise it will be a huge system, then we may not get the solution. So that is also one important thing. So then final system will have unique solution if the number of independent equation is same as the number of variables present in the final system. So that matrix has to be invertible, but in many cases it is not happening. Okay, then we need to think of generating some extra linearly independent equations. So suppose we have this example, we need to do the relinearization. So how we could do that? So we know that the multiplication of variable in a commutative operation in this relinearization method we use with the commutativity property to generate the more equations, because we have to generate the more equations, because our system of equation what we are getting is not invertible, I mean it's not giving the unique solution. So consider, for example, suppose we have a monomial, these terms, this nonlinear x1, x2, x3, x4. Now we can rewrite this monomial in a different way, like x1, x2, then x2, x3, x4, then x1, x3 and x2, x4, or x1, x4, x3, x4. Then we rename each of these different variable as y1i, because there are, so this is y12, this is y13. So like so if we have this term, say x1, x2, x3, x4, okay, so this can be written as x1, x2, so we can put this, or this is same as x1, x3, x2, x4, or this is same as x1, x4, x2, x3, okay. So now this we are denoting by yij. Yij is xi, xj. So we have many choice. So we can have corresponding equations. So we rename this, each of these different variable as yij is this. After substituting this new variable, we will get some new linear independent equations of this form. Okay. So then we then it has been observed, this is a real it has been observed that many equations generated by the relinearization algorithm are linearly independent. So once we got the linearly independent equations, then we solve this. Then if our system is consistent, then we can get a solution of this system, and we can get the corresponding secret key. So this is the this is called algebraic attack. We basically generate some equations, then we try to solve this equation by some of the method like Relinearization, Excel method, Gauss. So once we get a system of equation which is consistent, then we apply the Gauss elimination method to solve this. Okay, thank you.